Project 3.3.4, CHUMP, RAM, MUX, Address, Accumulator, and Control. This is the final CHUMP build. It includes some old parts like the 555 timer, the decoder circuit over here, the ALU, the PC, some new ones like the Address, the MUX, the Accumulator, the RAM, and then some refitted ones like the Program EEPROM and Control EEPROM, all of which I'll explain in a little bit. Right now, we have on Feinberg's original instruction set. It starts with the read 2, read here 8, and the constant 2. What that means is when we press the button, we'll see the address lines here. A 2 will light up. It's showing us that on RAM, there is right now a 15. This here is the accumulator LEDs, and these are the program counters. This one's showing that we're on the first instruction. Anyway, on address 2, there is a 15. If we go through, we can load it onto the accumulator. We'll then add 1 to it, add 1, and we'll get a 0 as shown on the accumulator. Now we're going to store that back to 2. We'll see now on address 2, there is a 0 matching the accumulator, and then we're going to go back to 0. Simple as that. Now, some of the new parts are the MUX, which is taking an input from this program ROM here, as well as the RAM. The program ROM has 4 output bits, 4 of which are going to the control EEPROM, and 4 of which are the constants going to the MUX. The control EEPROM is like a lookup table. It kind of, on its first 16 addresses, or A0 to A3, on its first 16 pages, if you want to think of it like that, there are all of the unique CHUMP instruction sets. So for each of those instruction sets, there are 8 control lines. These are going to the select of the ALU, carry in, mode, and then the accumulator select and the RAM select, which will set either of these as high impedance outputs if they're not necessary. The program ROM is being driven by the PC as usual here. And then the PC is getting its load bits. It's getting those from the MUX. And then those are also going, the outputs of the MUX are also going into the address register here. On a clock signal, on the clock tick, the address and the accumulator, which are both just D flip-flops, a hex D flip-flop and an octal D flip-flop, will latch whatever's on their input bits. So the address here goes to the address locations of RAM, and RAM I've seen has kind of acted like EEPROM in the sense of the addresses. There are some unique 4-bit values on those addresses. So when you call them, we saw it on the address here. When we called on 2, we could see that unique value for the RAM address 2 on these LEDs. They also have inverted outputs, which is why there's a not here. The A equals B flag is what's being used to for the go-to command to load the PC. There's a lot to explain here, but that's the basic functioning of it. So with this switch here, we can change over to the original code written in 3.3.1. So the first line here is to read 1. So 1 right now is a 0. If we look over, we can load it, right? And then we can read on 0. So right now 0 is a 1. Okay, so 0 is a 1 and 1 is a 0. Remember that. We're going to XOR it. We're going to store it to 1. We're going to read on 0. We're going to load that, and then we're going to read on 1. We're going to XOR that value, and we're going to store that to 0. Okay? And we're going to read 0. We're going to load it, and we're going to store that, or we're going to read 1, XOR that value, and store it to 1. You can now see 1, which we're reading right now, is a 1. 1 is a 1. And if we look at 0, it's a 0. And as you can see, the 0 was a 1 and the 1 was a 0, and we've now flipped the 2 variables, showing how you can swap 2 variables without the need for a third one. This is all for the CHUMP build. There's plenty more functions it can do, although not that many, considering it is a 4-bit processor, but there's not enough time to show them all. So I thank you all, and I hope you have a great day.